Recording is rolling. It is Thursday, October 6th. Oh, you guys do have that that one-to-one agreement. You guys got that one-to-one agreement on your desk? Right, so I put those on your desk before you guys walked in. Okay, looks like this right here. Right, so the school wants these back. The sooner the better. If you get these signed by your parents tonight, bring them back to tomorrow. That's actually the best thing you could do. But the deadline they have is by next Friday. So if you forget by tonight, tomorrow, then just bring it by next week. But you guys know next week's going to be a weird, choppy week. We don't have school Monday. We have a 3-day weekend. And you're not going to be in this classroom on Wednesday because I have to proctor PSDT. I don't know where you guys are going to be relocated, but I'll let you guys know when to figure that. Okay. You guys know tomorrow is the last day of quarter one. So definitely have all your assignments turned in and all your classes. For this class, the last 2 assignments are your dynamics homework and so it's chapter 4 puzzles. Here we go. They look like this. Okay. And also that take-home quiz. Okay. And most of you guys have already turned those in. Okay. So just if you haven't, then tomorrow's the last day. Okay. All right. Any questions about anything? Oh yeah. What's that? Yeah, all this new lab stuff, Centripetal Force Lab, I'm gonna put on the second quarter. Okay. All right. So you guys ready to move on to Centripetal Force Lab? All right, so here's what you guys did yesterday. You had the setup with a PVC pipe, a string, and a couple of Play-Doh canisters. Okay, and you're wheeling them around. And we're trying to figure out what is the relationship to keep this in balance. Okay, and by imbalance, maybe a more physics way to say that would be maybe this bottom canister could be in true static equilibrium. It has a weight down and a tension up that's in equilibrium. Okay. Now this top canister is constantly changing direction, which means it's accelerating. Special kind of acceleration called centripetal acceleration, provided by a centripetal force, which is the tension in the string. Okay, and we're trying to figure out, well, what is the relationship among these 4 variables? We narrowed it down. It's got to be these 4 variables. Okay, the weight of the hanging bucket, which is again providing the tension, which is providing the centripetal force. So we'll just call that basically the centripetal force, right? Okay. The mass of the swinging bucket, so to keep a mass moving in a circle. Okay. The speed, like how fast it's going, notice I'm calling this speed because it doesn't have constant velocity because the direction's changing. So, but it could have constant speed. Okay. And also the radius of the circle, like how big is the circle. Right. Those 4 variables, there's some relationship. And I split you guys into 3 groups, and you each investigated a pair of variables, the relationship. And the way we're doing this, just the way it works best, is to relate everything to speed, and then we're going to do something with that. Okay, right. So you guys remember that from yesterday? Right. And then you controlled a couple of variables, and you had one independent and related everything to speed. Okay. All right. So I had you guys do a write up for this too. Okay, here's how we're going to do this. I'm going to flip the screen over. We're going to put the graphs together. Now your own personal write up. Remember, you only have a third of. Whoops, gotta share my screen here. Everybody individually or within your groups only has a third of the story, right? And then we're going to put these 3 stories together and get the full picture, right? So when you guys did that 5-part write-up, if you did everything ideally, then your conclusion is just some kind of proportional relationship, just the 2 variables that you honed in on, right? Speed versus something, right? Right, should have a third of the story. Tell you what, if you want to amend your 5-part write-up as we're going along making these graphs, that's all right, because I know yesterday was a pretty action-packed day. All right, so let's get this going. All right, bring up this Excel page, move over here. All right. Okay. So first one I have is speed versus, right, now that F, you guys know capital F stands for force, and that could represent the centripetal force in this case, right? Like the tension in the string, which is also equivalent to what value that you guys were measuring yesterday? The weight of the hanging bucket. Okay, now a third of you guys were treating that as an independent variable. Let me see, show of hands. How many guys were changing out specifically the weight of the hanging bucket yesterday? Weight of the hanging bucket. Okay, so it looks like these 2 teams right here. Right, all right. So out of those 2 teams, who feels really confident about their data and wants to share your data?
We don't feel terribly confident in our data.
How about this team over here? Well, somebody's got to share their data. You only got 2 points? How many data points?
4 points.
4 data points? Yeah, I'm gonna just fill your data. Thank you. All right. All right. So for this paper, the weights, and remember these are in millinewtons. Right? We have 650 millinewtons, 1050 millinewtons, 860 millinewtons, and 980 millinewtons. Right. And then the corresponding speeds, controlling again for the mass of the swinging bucket and the radial size of the circle, as long as those were kept constant, okay, then this graph should work out pretty good. We're about to find out. 3.2. I think I mentioned this yesterday, but maybe I'll slip this in right before I start getting graphs. Is this is one of those labs that if you were really careful about getting your data, if you're really careful with the stopwatch, if you were really careful about keeping the size of the circle constant, if that was one of your control variables, if you weren't grabbing the bottom plate of the bucket and thereby adding an external force, okay, then if you did everything right, then these graphs are going to work out really nice and it's going to lead straight to the answer. On the other hand, if you did any of those things, the circle size was sloppy, or if you're like grabbing the bucket or anything like that, then these graphs won't turn out so pretty. But we're gonna see. We're gonna see how this looks here. All right, so here's the corresponding speeds in meters per second. These are all meters per second. Okay. So thank you for sharing that one. Oh, guys, when you see that title, V versus F, which of those variables is the vertical axis? That's V, right? It's always Y versus X, right? Vertical versus horizontal. This is V in meters per second. Now, when you guys make your graphs, to label this vertical axis V, and as the unit, it would be meters per second. So this is V in meters per second. That's how I always draw the graphs every time I draw them on the projector, right? V in meters per second. And the horizontal axis, this is the corresponding centripetal force, and this could be in millinewtons today, right? Millinewtons. Right, all right. All right, so give you guys some graph spaces. Should be definitely copying this one down if yours says borrow data to complete this graph, right? Because there you go. There's your data right there that you are borrowing if you didn't get it yesterday. Okay? Which is probably about 2/3 of you guys. Okay. Right, V versus F. Okay. All right, so we got to figure out what is that relationship? What's going on there? Right. How about this? Let's step back a step and think, what would you have hypothesized? Guys, if you're making that hanging canister heavier, 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 do you think you have to swing faster or slower to maintain balance?
Faster?
Yeah, probably faster, right? So there should be some kind of upward trend with this data, right? Ideally. All right, let me show you guys the ideal solution. Oh, this is Excel page not going to open. Oh, here we go. All right, there you go. Like if you had like perfect data, it would have taken that shape, right? Now those exact numbers depending on exactly what is. All right, so that's the ideal answer right there. Oh, guys, what shape is that? That does look like a square root, doesn't it? Right. So let's assume that it is a square root. Now, if it is a square root, which it probably is, it definitely looks like a square root. Right? I mean, if it's not a square root, maybe it's a cube root or a fourth root or something else, right? But what it looks like is going on. V in meters per second. You guys have a bunch of numbers. Okay. Force, that's the weight, but it's also representing centripetal force in millinewtons. A bunch of numbers. Okay. It looks like we have some kind of square root type relationship going on right here, right? Okay. So I would say that V is proportional to the square root of the force we got. In fact, if you had this particular experiment, again, it looks like two groups did, right? That would have been the ideal conclusion to this whole lab, right? This is your third of the story, right? This particular proportionality. Okay. Now, you guys remember, even go back to the very first week in this class, you guys remember Grafham's properties of circles, right? Like area of a circle is pi r squared, right? and it said graph A versus R, and you guys got a parabola. And I said graph A versus R squared, like a manipulated axis, and it straighten out into a straight line. We're going to do the exact same trick here. I mean, this is a trick we've done a few times. That's just another example of that, right? That's what happens when you square both sides of this equation. You get v squared is proportional to f. Did you guys see that? Right, just square both sides. Okay. Notice this is not a complete equation. That little squiggle right there, that's kind of like an equal sign, but it's not a full equation. It's like I'm leaving parts of the equation off. It's just part of the story, right? So, but the algebra rules still apply. You can still square both sides, right? Right. This is a trick you have to know for AP physics. Almost certainly you're going to get an FRQ that involves that trick. Okay. So we're going to make a new graph. And on the vertical axis, I'm not going to put v. I'm going to put v squared. Right? It's kind of an abstract idea. Wouldn't this be in meters squared per second squared? Okay. And the horizontal axis will go ahead and leave. It's just plain force and millinewtons. Okay. Now, if your hunch was right that the first graph is truly a square root graph, square root relationship, then what should v squared versus f look like?
Linear.
Linear. Yeah. It should line up in a straight line. Okay. Now, I know my paper has no numbers on it. I'm just showing you guys the general idea. But we're going to switch back over and see if that's, and right before I switch back over. Here. On the back of the slide page, you guys see these three graphs where everything, they're larger because it's where everything's feeding into. And the top one says v squared versus weight hanging. Hey, that is this, isn't it? Right? Okay, you guys see where this is going? Actually, all three of these graphs are v squared versus something, right? So see if you can sort of relate everything to either v or v squared, then see how all the puzzle pieces are going to click in at the very end. Can I look ahead a little bit? All right, so let's switch back over to the Excel page. Okay. I'll go ahead and just show you guys the ideal solution. Right. So suppose those were your numbers right there. Then if you square all the v's, guys, 1 squared is 1, 2 squared is 4, 3 squared is 9, and so on all the way down. Right. But the forces would stay the exact same. Got right. Look here, all the forces are the same, but oh, look at that. 1, 4, 9, 16. Right. If you square up, right? Oh, look at that. And all the points pretty well lined up into a straight line, don't they? Right, you guys see that? Right. Right, so the top graph on the back of that half page, go ahead and just copy that one down. Okay. So you got v squared on the vertical axis. You got, and that's in meters squared per second squared, kind of abstract idea. Okay. You got force in millinewtons on the horizontal axis. Right. Origin point is 0, 0. Right, and then all those points pretty well line up in a straight line. And zoop, just do a straight line relationship. Okay. So there's a linear relationship between the square of the speed and the weight of the bucket, which again is the centripetal force. The force that's allowing that circular motion. All right, you guys got that graph? Okay. All right, so everybody should have at least 2 graphs done at this point. You could, on the front of that page, you guys got the top left graph finish, just v versus f, and on the back, you have the very top graph finished, v squared versus f, and that one's just a linear relationship. You guys got that? Okay. All right. Next graph. Let me see how your guys' data actually turned out. See how close it was. Okay. That's all right. So the next one, v versus m. Now, I know there are sort of like 2 masses in question, but when you just see m, you guys know that refers to the swinging canister, right? The one that's swinging around in a circle, right? Like that is mass that is being accelerated, right? That has the centripetal force acting on it, that is actually moving in a circle. Okay. So this is the, let's see, show of hands. How many guys were in a team that was changing? Where is this? I want help. Stop. How many guys were in a team that was changing out the mass of the swinging canister? Right. So it looks like these 2 teams right here. Right. All right. You guys feel pretty confident about your data? Yeah, kind of. All right. What's your? Here. I need somebody's paper. That's this one. Ooh, I think this looks pretty good. I got confidence in this group. Let's see. See if you fair me. No. All right, so the swinging masses, these are in grams. We got 26 grams, 29 grams, 36, 39, and 46. Okay. And what were the corresponding speeds? 12.23, or sorry, no, sorry, that's the square speed. Scratch that. Okay. 3.5 meters per second, 3.3, 3.3, 3.79, 2.71. Oh, I meant to ask guys before I plug those numbers, because if you're making that top swinging mass heavier, 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 how do you think you have to swing it? I think not as fast, right? Right? Like here, or let's go the other way. What if you took the top plate of canister and just left it empty, so it was just a little tiny 6 grams? Do you have to go spin it really fast? If it was really light, or just like the other way? So heavier is slower, lighter is faster. Oh yeah, go. Okay. I like this data right here because this is like an inverse relationship, right? That's that inverse relationship that I'm talking about. This is actually ideally what you guys should have gotten, right? That inverse type relationship. Yeah.
That means 0, 0 is not a point.
Correct. 0, 0 is not a point. Okay. Because guys, if the top plate of canister that was swinging around a circle, if you took its mass all the way down to 0, right, just like attach a paperclip there, when you have to spin it extremely fast, just like helicopter speed, like flash, right? Wouldn't that be like a vertical asymptote right here, right? So if you have a little tiny canister you're swinging around in a circle, it has to be a huge speed, right? So yeah, there's definitely some kind of inverse relationship going on here. Okay, right. So everybody, I'm most of the way through copying that. This is the bottom left graph on the front, V versus mass swinging. Okay, so on the vertical axis, V. In meters per second, it goes up to about 4 meters per second. And on the horizontal axis, in grams, this is mass in grams, goes up to about 50 grams. Right, so scale those axes, label and scale those axes, put the points about where they go, and yeah, inverse relationship. Yeah, as one variable gets bigger, the other gets smaller. All right, so let's say we'll ultimately want to piece together some kind of general formula, right? We have a third of the story already from before. We're getting this third of the story. We need to somehow linearize this data. Now, if there is an inverse relationship, don't we have to like take the reciprocal of something? Right? Now, I know the first puzzle piece we have from before has like v squared versus something. So maybe I'll go ahead and leave the v alone and maybe take the reciprocal of the mass, right? I mean, there's one of two ways. You got to take the reciprocal of something, right? So what if we did v versus 1 over mass and say, because that could possibly straighten it out, right? Maybe it will, maybe it won't, but there's some kind of reciprocal going on. So you guys see the bottom right graph on the lab page? Okay, so you guys just did the bottom left graph. Okay, that's the one that's on the screen right now. But what about the bottom right graph? See where it says v versus 1 over m? That could possibly linearize a reciprocal graph, right? An inverse relationship. Okay. Let's see. Is it here? It is. V versus 1 over m. Actually, that's what that one should look like too. So that's good. That's good. Right now, all that's gone on here. These v's are just copy pasted, like 3.5, 3.13, 3.5, 3.13. Those are just copy pasted, and the masses are all reciprocals. See over the little tiny decimals, right? And look at that, right? That's about what that should look like. Right. So everybody's right now making the bottom right graph on your lab page. One says v versus 1 over m. Okay. So v is the vertical axis. That's still in meters per second, and 1 over m. Ooh, that's like 1 over grams. Okay. Now, do you guys think that data is actually linearized exactly? I don't think so. Do you think it looks kind of like a what relationship do you think it is if it's not linear? Maybe like a sideways parabola, right? Oh, sideways parabola. Could it be like a square root? Right? Like a square root relationship? I think that looks a lot like a square root type relationship. Okay, can you guys imagine like a square root curve, like sweeping through those points pretty much? Okay. So, maybe it's not exactly linearized, but it is a step closer to that. Okay. So we're at least heading in the right direction. Okay. In fact, if this is a square root relationship, we already linearized the square root relationship earlier in this class, right? Did we just like square square the v, right? So if you do v squared versus 1 over m, that should like straighten out into a straight line relationship, right? All right, so all right, you guys ready for next graph? All right, so flip the lab page over, and the middle graph on the back says v squared versus 1 over m. Okay, see that? Okay, all is constant, of course. Okay. And that's what we're about to do right here. Oh, before you guys see the graph, see the table right there, v squared versus 1 over m. Okay, now if this works, it should line up in a straight line. We're about to find out. Moment of truth. Oh, look at that straight line through the origin. That's a direct relationship right there. Look at that. That is pretty well exactly what that should look like. All right, nice job. V squared versus 1 over m. Okay. So now we know that the square of the speed is in fact directly proportional to the reciprocal of the mass. Okay. Let's say like if you triple the reciprocal of the mass, you're also going to triple the square of the speed. Right? So we have two manipulated axes. Right? That was like a two-step process. And so while you guys are copying that down, remind you guys how we got here. Okay. We did oh yeah, go ahead.
How come there's one at 0, 0?
0, 0. Okay. So let's say you had a very let's think about some terms of extremes. You got a very large mass or a very small mass, right? What if you have a very large mass that's swinging around a circle? Don't you have to swing extremely slowly, right? So if you have a very large mass, guys, what is 1 over a very large number? That's very close to what? 0, right? Like the larger the denominator, the closer to 0 the fraction gets, right? And then okay, well, just take the square root of that or square it however you go up. Like 0 square root of 0 square root of 0 is it's still gonna be 0. So it's gonna approach 0, 0, right? Maybe this point doesn't truly exist, but it's it would like approach that point, right? And if you go the other way, what if you have like just a paper clip going around? We have to like just like crazy fast, like a dentist drill, right? And if that's true for a very tiny mass, oh guys, what's 1 over a very tiny number? So that would blow up really huge, right? Let's see. So how would that go? Here we go. So if you had actually that would be like moving to the right on the graph is what that would be. All right. So let's take the opposite case. Okay. So my first example is actually better. If you have a large mass, that would say something about the origin point 0, 0. Okay. You guys got that graph? Okay. Are we good? All right. So we have 2/3 of the story. We just need one last puzzle piece, and that's the radius of the circle. Right. Let's do some quick hypothesizing for we run to this last graph. So as this one's a little tricky to think about. How about this? So you have everything in balance, and you got a equal size circle or whatever, blah, 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 right? What if you spin it a little bit faster? Like you're going to put a little bit more oomph into my spin, right? What happens to the size of the circle then? Would get a little bit bigger, right? So let's see, faster speeds and larger radius. There should be some kind of relationship like that, right? All right. Who was in one of those groups? All right, yeah. Go ahead. Actually, again, already did too. Thank you. All right, so we're going into the last part of the story. We got wait a minute. V versus here we are. V versus R. Right. So as you were changing the radial size of the circle, how did the corresponding speed? Right. So here are the radial sizes in meters. Got 0.27 meters, 0.28 meters, 0.23, and 0.28. Okay. Now
we might have to redo on this one because see how there's not a whole lot of variability in the radial size, right? It only changed by like 5 or 10%. All right. Let's see how this plays out anyway. But I might grab somebody else's data. Let's see 4.3, 0.6, 0.8. Yeah, see, it's all kind of like bunched up in a little ball there, so it's kind of hard to make sense of that. Let me do this. Yeah, grab another group's data. Thank you for sharing that. Okay. So who was in another group? All right, so feel free to get back to that. Try it out. Try us out. All right, so we got radial sizes of this 0.34 meters, 0.43 meters, 0.59, and 0.31. Okay, so there's a good variability here. Let's see what happened to the speeds here. 4.46, 5.49, 4.3. Is that a 4? I think.
Yeah.
Okay. All right. Yeah. Let's run with that. I think it'll be close enough. All right. Thank you. All right. So we sort of hypothesized. We were saying, well, it kind of makes logical sense that larger radius should be a greater speed. Right. I know there's only like 4 data points here, but kind of an upwardish trend, right? Maybe. I don't know. Kind of hard to say, but that's ideally how it would work out. Hey, do you think this one is possibly a square root relationship also? Like, suppose we had, instead of 4 points, what if we had like 100 points, right? And found like some overall trend. Do you think overall it starts to bend to like a square root type shape? Okay. All right, so you guys are copying this one down, right? It's the last graph on the front, well, the top right graph on the front. One you hadn't done yet otherwise. So V versus R, all else constant. Okay. So for the constant, this is to say that the 2 Plato canisters were untouched during this entire experiment, right? The mass and the weight were not changed. Right? So different size circles correspond to different speeds. Yeah, and I could kind of imagine maybe that is a square root type relationship going on there. Okay. Right? Guys up there? All right. Now, if that is again a square root relationship, well, we've already done that twice earlier today. Right. So if we want to linearize this data, can we do like V squared versus R? And maybe that should straighten out into a straight line. Right. All right. Are you guys ready for the very last graph? Oh, yeah. Yeah, it's a square root. Yeah, square root relationship. Okay. Gotta go with that. Great. All right. So on the back of your lab page, at the very bottom, see where it says V squared versus R? Right. Of course, it would be that if this is a square root relationship. Right, so let's do the very last graph. Right, so see V squared versus R. Right, so all the radius values are just copy pasted, but the V's are all squared. Right. Now let's see if this lines up into a straight line. Let's imagine it does. Oh yeah. Let's see if it actually. Yeah, we'll call that a direct relationship. How about that? Direct relationship. All right, so for V squared versus R, you guys have the vertical axis labeled V squared, and that's in meters squared per second squared. You guys have the horizontal axis labeled R, and that's in meters. You have them scaled, so like 0 to 30 something and 0 to 1 basically. Okay. So the points about where they go, and then direct relationship. Zoop. All right, you guys got all the graphs now? Right, so you guys should have all the graphs. Let me switch back over here. Right, so these last three graphs are leading straight into the answer. These couple of boxes at the end are that's where we're going to set up this formula. Right, so here's one of the relationships: b squared is proportional to f. Right, that was the first graph, first of those three graphs. So the square of the speed is directly proportional to the centripetal force. Okay. You guys also got the square of the speed is proportional to the reciprocal of the swinging mass. And also the square of the speed is directly proportional to the radius, right? Because b versus r was square root, so b squared versus r linearizes. Right. Now, since everything is related to b squared, can we put this all together into one giant proportionality? Here's a third of the story. Here's a third of the story. Here's a third of the story. Can we bring all the pieces together? It's a b squared is proportional to, it's going to be a giant fraction. How's this fraction going to go? Yeah, f times r over m. There's where it all comes together, right? Okay. Right. Now, you guys know b refers to speed, the m refers to the mass that's has the centripetal force acting on it, going around a circle. R is the radial size of the circle, right? Raised to curvature. Okay. And this f really refers to centripetal force, doesn't it? Right? It was the weight of the hanging bucket in the experiment that created the tension, which created the tension acted out the centripetal force, right? Right. So if you wanted an expression that was centripetal force as a function of all those other things, can you just take this expression and rearrange it algebraically? Okay. And what would that look like? Centripetal force would be proportional to what? mv squared over r. Bing, winner, right there. Okay. In fact, I'll go one more step, which is that if you take the slopes of these three lines and multiply them together, you actually get one. Like no units, no numbers. It's just that slope times that slope times that slope is one, which tells you that this isn't just proportional. Actually, it's an exact equation. So I can say this: centripetal force is equal to mv squared over r. Right, and that is the answer to this lab. Right. You guys see those two boxes at the bottom? So it's how are the four variables related? We can say, well, b squared is proportional to fr over m. Therefore, solve for f. Well, force is proportional to mv squared over r. And it turns out that it is an exact equation. Okay, that's another way to say proportional. Okay, so I've seen both ways to say proportional. So. Okay. All right. You guys good there? All right. So, it turns out that anything that's on a curved path, well, if it's on a curved path, there must be some force that's causing it to go around a curve, right? That's what's hinted by Newton's first law of motion, right? Right. Things only ever want to move in straight lines. Okay. And what is the value of that force keeping something on a curved path? Well, if you know the radius of curvature of the path, and you know the mass of the object that's being deflected, you know how fast it's going, you just always pop it into that expression. Okay. Now I should tell you guys that centripetal force is not like a pure force unto itself. Like there's always some force that's providing that centripetal force or some net force. Like in the example that you guys did yesterday, it could be the tension in the string, which is equivalent to the weight of the hanging Play-Doh bucket. Right? It could be the centripetal force could be. How about this? What if I have a turntable? I stack a lab mass on it, and it spins around a circle. Right? Guys, if there was no friction on this tabletop, then well, I guess this wouldn't actually move at all. But if it was moving, it would just want to move in a straight line, like fly off, wouldn't it? Okay. So isn't there some friction that's holding this like in a circle? Okay. And you could call that friction the centripetal force. The centripetal force in this case is provided by the friction between, say, this surface and this surface, right? So we had. Okay, so that's what's holding that in a circle. I have whoops, stuck up here. I know the mass of this guy. This guy has a mass of 0.5 kilograms. I know the radius of curvature looks like 10 centimeters. I could call it 0.1 meters, right? This is from the center points, this thing's spin around. Okay. And if I can figure out how fast it's going, which you guys found out a way yesterday, you guys did circumference of the circle divided by time period, right? I could have all the elements. I could probably pretty quickly solve this right here. Actually, I have a lab lined up for you guys eventually I want to do, but that's how we'll get to that, hopefully. All right, you guys that thing? Oh, let's do this. I know you guys want to score yourselves with that AP rubric too, so we're getting there. But let's real fast do number 27 from your guys' homework page. Number 2. Okay. We'll just do this one. Okay. An air putt of mass 0.25 kilograms, that's this guy right here, is tied to a string that's allowed to revolve in a circle. Oh, radius of 1 meter on a frictionless horizontal table. Hey, is that like an air hockey table? Right? The other end of the string passes through a hole in the center, and mass 2, they've also designated 1 kilogram, is tied to it. The suspended mass then remains in equilibrium while the puck on the tabletop revolves. Right? Now, equilibrium, you guys know that means all the forces balance. They're talking about M2. M2 has a weight down and a tension up that are balancing out. Right? That's why M2 is in true static equilibrium. Okay. Now, M1, guys, is M1 in equilibrium? No, there's a net force on it. The net force is the tension. Okay. Hey, guys, which direction does the centripetal force always point? Towards the center of the circle, right? Isn't this tension in the string pulling M1 towards the center of the circle? In fact, if M1 was not in motion, if it just started from rest, it would just be drawn straight to the center, just vacuum straight in, right? Okay. But because it has like tangential inertia, right, it's moving off to the side. Right? A lot of stuff is dynamic, right? Okay. So question, what is the tension in the string? What is the horizontal force acting on the puck? And what is the speed of the puck? Right? Well, guys, the tension in the string, wouldn't that just be equivalent to the weight of M2, which is about 10 newtons, because the mass of the block is 1 kilogram, 10 newtons, right? So bam, there's question A. It's just the weight of M2. Okay. Question B, what is the horizontal force acting on the puck? Well, that's just the same force, isn't it? It's also the tension in the string, which again, it's equivalent to the weight of M2. So that's also the answer to part B. So we just knocked out part A and part B, right? Just the weight of M2, right? Now part C, what is the speed of the puck? Now here's where it gets interesting, because you guys get to actually apply the answer to the lab you just did. This right here. Centripetal force is mv squared over r. Oh, I meant to also point this out, where this is on your AP equations. It's sort of on your AP equations, but a little bit in disguise. You guys see this one right here? It says centripetal acceleration is v squared over r. You guys see that one? You guys see that's just a manipulated version of what you just found in your lab, right? Because isn't acceleration just force divided by mass? So, you guys see that's really the same thing, just like one step away. You see that? Okay. So AP equations don't have this one exactly spelled out, but they have one that's adjacent to it spelled out. Okay. All right, so that's there. Okay. All right, so let's do this then. Got maybe I'll change the values just to make this a little bit more interesting. I'll call this mass A. I'll make this guy 3 kilograms. Okay, here's the string. I'll call this guy mass B is equal to like 7 kilograms. How about that? Okay, and this mass A is moving in a circle, so it must have some speed v. Okay. It's got some radial size. Let's say the radius is 0.60 meters. Okay. All right, so I got some numbers. There should be enough information there if you assume you're on Earth to answer that question. So I'm going to go centripetal force is mv squared over r. Of course, we're talking about ma, right? M sub a. Okay. We're solving for v. What's the speed? Okay. That's the question. Right. Hey, can we solve in terms of variables first? Okay. So if you take centripetal force, multiply by the radius of curvature, divide by the mass of the block, that would be the speed squared. Okay. So wouldn't the speed just be the square root of all that fun stuff? Like that? Is that true? Okay. Just
little bit of algebra switch around just in terms of variables. Okay, you guys solve in terms of variables, right? Okay. Okay. And then pop in some numbers. You could have popped in the numbers to start with, but it's good practice to be able to do it this way. Okay. Now, remember, the centripetal force is the tension of the string, which is equivalent to the weight of this block. Which, guys, what's the weight of this block? 70 newtons. So I'm going to put 70 newtons right here. Okay, so that is what's acting as the centripetal force, 70 newtons. Radius of curvature at 0.60 meters. Maybe I should have said 60 centimeters, but you guys could have converted that anyway, right? It's divided by 100. Okay. And then we've got 3 kilograms. That's actually the centripetal force is acting on. Okay. So we got a big old square root. 70 times 0.6 on 3. All right, looking at right now paper. Well, here's what it ends up being. 3.74 meters per second. All right. So if you like point a radar gun at it, that's how fast, that's its instantaneous speed. Okay, as it's going around. Okay, is that all right? Okay. You guys good there? Okay. And of course, you guys have different numbers for 27, but it's the same way to solve it, right? All right. Next thing. So, who's got any questions so far? Any questions? All right, so we got about 8 minutes of class left, so that's perfect for this right here. All right, AP scoring rubric. So you guys wrote up an AP style write-up for this lab. Remember, you only have, each of you has a third of the story, because we had to put 3 experiments together. And I put one of these packets on everybody's desk so you could score yourselves. Now, you guys got those colored pencils on your desk, right? So here's one experiment, here's one experiment, here's one experiment. Just for the video, I'm going to recap how this works. So there's a question. What the question is, goes back to this question you're trying to answer yesterday. But remember, each of you took 1 of 3 perspectives on it. So there's really 1 of 3 questions that each of you were honed in on, right? Okay. Either this relationship, or this relationship, holding the other variables constant. Okay. One section, measuring tools. So I bet everybody at some point either used, or it was implied that you used some kind of ruler or meter stick. I bet you guys used a stopwatch at some point. And if you didn't use a scale or a balance or a triple beam balance, then you would have added up the masses. So that would have been a good tool to have too, right? Okay. Then data gathering procedure. So how did you measure what variables using what measuring tools? Always something AP's looking for. Okay. So there's 1 point for basic description of lab setup. I said put a string through a plastic tube, secure the canister to the end of the string, whirl the swinging canister in a horizontal circle so that the weight of the other canister, the hanging weight, provides a centripetal force that holds the swinging canister in a circle, constant radius. Okay. So 1 point for basically describing the setup. Okay. Then there's a bunch of individual points for going about gathering your data. Now here's where the story branches out into the 3 different paths. Okay. And then the next section is analysis. So this is where equations and graphs come into play. Now, you guys had a linearization situation, right? Each of you, at some point, right, had one of these starting graphs and had to linearize the data by manipulating axes, right? So that's your data analysis. So one group should have gotten b squared is proportional to the radius. That's this one here. One group got b squared is proportional to the reciprocal of the mass. That's this one right here. And one group got b squared proportional to the hanging weight, which was providing the centripetal force, which is this one right here. Okay. And then that would also lead straight to your conclusion. So you had one of those 3 conclusions. If you put those 3 conclusions back together, then you get the full equation. Centripetal force is mv squared over r. So go ahead and take the rest of the class, score yourselves out of 12. When you finish, pop that in the grade tray. And then that's what we got today.